Good evening, afternoon, morning. So last video we have discussed about differentiation. Okay, so we've discussed about differentiation of several functions, right? Specifically, we talked about log functions and of course exponents and hyperbolic functions, right? We've already discussed about the derivatives of these three category of functions and also did some examples on them, right? So we've already worked on these examples. Now, as promised, this tutorial video will focus more on parametric functions and implicit functions, all right? So parametric and implicit functions. So this would be what we're focusing today. So this is what's going to be focused on, right? Okay, so without further ado, let me give a brief idea about what these functions are and how do we differentiate them actually. Okay, so let's talk about parametric functions. Okay, first of all, what are parametric functions? So for parametric functions, the thing about parametric functions is actually the name itself, parameter. Okay, so it's basically from related to the word parametric. Okay, we're talking about the word parameter. So a function, okay, whether it's x or y, can be represented in some parameter itself. Okay, what I'm trying to say is, for example, if we have a function x represented in terms of a parameter like t, let's say t squared, okay, and we have another function right here y that's represented by cosine squared t. Okay, so you can see that x and y are represented by the parameter t. Okay, so this parameter in our case is t. Okay, and functions x and y, all right, are represented by a parameter t. Okay, so that's basically what parametric functions are all about. It's when you're having like your x and y functions, they're represented by another parameter such as t, or maybe you can have another letter like v or u or w. It doesn't matter, the parameter is really up to you. It's actually not it is your choice. Okay, it's more of like your decision, your choice. Okay, so that's the idea of parameters itself. Okay, and in many cases we sometimes actually express x in terms of a parameter and y in terms of a parameter itself. Let's say, for example, you are doing how do I say this? Let's say you're collecting data. Okay, you're collecting maybe collecting, let's say, data for let's say maybe an environment, for instance. Okay, maybe for example a particular environment. Let's just pretend we're collecting data for a certain environment. Okay, for environmental studies. Okay, let's just say for environmental studies. Okay, so maybe your x, okay, could represent humidity. Okay, your x could represent humidity of the environment itself. Your y could represent maybe air quality. Okay, for instance. And we know that humidity and air quality are related by a particular parameter. Okay, and this parameter may be the temperature. We can call it the air temperature. Okay, so it's related by this parameter called the air temperature. All right, so we can represent the humidity as a function of temperature. Okay, so for instance, maybe it could be x is equals to 3t cubed, for instance. Okay, and the air quality might be related to the air temperature by this relation right here, which is 4 over T squared. Okay, and we also are trying to find the relationship between x and y. For example, you want to find the derivative of humidity with respect to air quality. Alright, how does humidity change with air quality? That's the meaning of a derivative, right? So derivative actually talking about how does humidity change with air quality, for instance, okay? With air quality. So we want to find that out. So how do we find out the dy dx actually? Right, I'm gonna have to erase a bit of stuff here, so let me just erase this. Okay, so in this case, okay, let me put it back in here. Okay, so essentially we know to find dy dx is just dy dt times dt over dx. So it's basically chain rule, right? It comes back to the chain rule. And of course, why is it chain rule? Because you know dt would cancel out, right? That's how I'll get your dy dx. And dy dt is very simple. You already have your function y in terms of t. Very easy to get it. But how about your dt dx? How are you going to get your dt dx? How are you going to get your dt dx? And this is where the inverse rule comes in. So dt over dx is basically 1 over dx dt. Okay, so this is actually your inverse rule. Okay, this is your inverse rule. Alright, so from the inverse rule you'll be able to get dt dx, and then you're going to cross multiply with dy dt. Or you could probably just simplify this, alright? To find dy dx, it would just be dy dt multiply divide by dx dt. Alright? Dy dt divide by dx dt. Okay? So it becomes fairly straightforward. So in this case, if we were to do the differentiation, so dy dt would be negative 8 to the power of t to the power of 3, negative 3, divided by 9t squared. Okay, so that would be negative 8 over t cubed, right? T times 3 cubed times 1 over 9t squared. And you know, if you were to simplify it, it'd be negative 8 over 9 t to the power of 5. So this is your dy dx actually. Okay, so this is our dy dx. So this is our, okay, that's your dy dx. Okay, so now we've managed to find out how does the humidity change with respect to air quality. Basically is just negative 8/9 over t to the power of 5, temperature to the power, the fifth power basically. Okay, so that's basically the general idea of parametric functions, and I've just given a very dumbed down example, but there are many examples where x and y would basically be a measure of real world phenomena related to a specific parameter. Okay, and that's how they'll end up being represented. And sometimes in science, whether it's engineering or any other science fields, we want to see how does the humidity or how does the variable y relate to the variable x. That's the whole idea of the derivative itself, and this is the function that allow us to explore this relationship. Okay, so yeah, that's the idea of parametric function. Now let's talk about a second kind of functions here, implicit functions. Okay, so implicit function, let me just erase this real quick. Okay, let me just release the brush a bit. Okay. So for implicit functions right here, yeah? So for implicit functions, okay, so for implicit functions, how we will write these functions is not your typical function, because normally your typical function, or what we call as explicit functions, okay, so typical or explicit functions would look something like this, right? It would be y equals to sine hyperbolic x plus x cube plus ln x. Okay, so this is your explicit function. And why is it called explicit here is because we know that y is expressed in terms of x. Okay, in terms of x. So we know that one variable is expressed in terms of another. So one variable expressed in terms of another. Expressed in terms of another. Okay, so that is basically the generic idea of explicit functions. But when we talk about implicit functions right now, okay, implicit functions. So implicit functions, it's not very clear cut. We do not know what is variables expressed out of. For instance, let's say x squared plus y squared minus ln y equals 0. Okay, so this is a bit trickier because we do not know what is expressed in terms of what. No, so there's no clear indication of which variable representing which variable. Which variable is being expressed in another variable, and expressed in terms of other variable, right? Other variable. So it's not very clear because it's just simply a straight up equation with a mix of variables. Okay, so you have like different variables here. You obviously have your x squared right here, and then I'm gonna circle in white. You have your y squared, you have your ln y. So you see they are completely different. They're expressed, in such a way that you do not know whether it's y expressed in terms of x. So you do not know if y is expressed in terms of x or x expressed in terms of y. We don't know. So we don't know. I don't know. Okay, so that is what we call an implicit functions, and there are actually a lot of cases where we do implicit functions as well. Okay, like for example, some special curves or graphs represent, for example, the circle. If I'm not mistaken, the circle equation was x squared. Sorry, no. If I'm not mistaken, for the circle equation, for example, was x minus a squared plus y minus b squared, something like that, equals to 0. That was the circle equation. Let me just have a look back again at it, because it's been a while since I remember the circle equation. Let's see. Okay, so right. Well, let me just check real quick, yeah, on the circle equation. I might have forgotten a bit about it. Just a few minutes, yeah, just give me some time. Circle graph equation. Let's see. Oh, correct. Except just one thing, I made a small mistake actually on the circle equation. I forgot to put a R here. r square. Okay, so yeah, that's actually one case, right, of a circle equation. So the general form is correct, just forgot to put r square, where r is your radius. Okay, and there's many other graphs obviously out there in calculus where it will be expressed in a form like this, like for example x squared y minus log xy equals to 5. Okay, so you can obviously plot these graphs, don't get me wrong. You just plug in the values of x and y that you want, and you see if they satisfy this 5 or not. Okay, you satisfy, and then you obviously can plot the points. It's really easy to plot. It's very easy to plot such curves. Okay, so randomly just plot here, for example. Maybe for example it looks something like, I don't know, maybe it's a limit, I guess. Yeah, probably like maybe here or something like that. But anyways, so there's many graphs, you know, and many phenomena that you don't really describe within very typical explicit manner. Okay, you don't, there's many phenomena that you wouldn't really be using in an explicit manner. For example, like I said, the circle graph is one famous example you've learned in school or in college about this. And there are even sometimes functions like this, or even more complicated functions which are expressed in this manner, in an implicit form. Okay, rather than a implicit form, yeah, rather than an explicit form. So how do we deal with such function? How do we find the derivative of such functions? Okay, let me just clear up and show you an example, okay, of an explicit function that we could do. Okay, so let's say we have a function right here, x squared plus y squared minus 2x plus 4y, okay, minus 20 equals 0. Okay, so this is actually a circle equation, by the way. This is actually going to give you a circle. So this is a circle equation, and we want to find the derivative, right? We want to find the dy dx. Okay, so how do you find the dy dx of this circle equation? So what are we going to do is we will take the derivative, okay, the generic derivative, so the d dx, okay, without the y in it, on both sides of the equation. So x squared plus y squared minus 2x plus 4y minus 20 equals a derivative on 0. Okay, then as we take the derivative with respect to x, okay, we take the derivative with respect to the x inside the function. It'd be quite straightforward actually. We'll end up having what? We'll end up having 2x minus 2. Okay, now how about y? How are we going to deal with terms of y? And it's fairly quite simple, really. It's just we differentiate the y. So in case of y, it'll be 2y, right? But we'll be adding this term here. That would be your dy over dx. So when you differentiate any terms with respect to y, we'll be multiplying with the dy dx in it. And since 20 is just a constant, okay, as well as 0, so they can be forgotten, okay? So they'll obviously be 0, right, when you do the differentiation. So 0, 0, 20, 0. So at the end of the day, it becomes 0. Okay, so once you have already gotten your differentiation, what is the next step actually? Of course, we're going to rearrange the functions. So 2x minus 2 is equals to negative 2y dy over dx minus 4 dy over dx. So we're going to of course represent in terms of dy over dx. So it's just 2x minus 2 equals to dy over dx equal, oops, I made a mistake here. It's not supposed to be an equal sign. It's more of okay, I don't make series are too big. It's more of bracket, you know, parentheses. So 2y minus 4. So therefore your dy dx is just 2x minus 2 over negative 2y minus 4. And of course you can simplify it. You can just say just x minus 1 over negative y minus 2, and yeah, you can say it like that as well, you know, it's no problem at all. So that is your dy over dx. Okay, and you might be wondering, is it okay to leave our dy over dx in terms of x and y? And the answer is yes, it is completely fine. So there is no problem at all whatsoever, because for implicit functions, since the functions expressed in terms of an implicit manner, so therefore the derivatives itself of this function will also be in an implicit manner as well. Okay, so there is no problem at all. So you know, if it's a function in terms of fxy equals whatever constant, then once you find the derivative of it, then dy over dx, it would be something like a, you know, a derivative of x and y together, obviously, right, in some sense. So it's completely okay. All right, so I think that's the generic idea of implicit functions. Now there is one last thing I want to add actually before we jump on to the question straight away. That is related to implicit functions too as well, but we're going to also talk about it. Okay, alright. So one last thing I'll talk about is logarithmic differentiation. Okay, logarithmic differentiation. Okay, so you might be a bit confused and wondering, but didn't we talked about differentiating logarithms in the previous videos? And no, I'm not talking about ln x or log x. We know what the derivatives are of these two functions, right? Just to recap, when you differentiate ln x is just 1 over x, and for log x is just simply 1 over x times log of e. Okay, that's basically the derivative, but we're not talking about that right now. We're not interested in this. Actually, this is to do more of implicit differentiation actually, and you'll see why. So let's say we have a function here, so y equals to sine x to the power of x, and the question wants you to find dy dx. Okay, how are you going to find dy dx? How are you going to find it? So you might tell me that why not we use the chain rule? Okay, and yeah, that might work, and let's give it a try and see how it works. So for this particular function, if I take the sine x as my u in this case, so if I take my sine x as my u, so u would be sine x, right, and x would be sine inverse u, right, and we know that, well, du dx would be cosine of x. Okay, that sounds very good, isn't it? And that'll be pretty okay. But the problem is our y, once we write in terms of u, it'll be what? It'll be u to the power of sine inverse u. Okay, and this has become a much more complicated problem because you cannot solve it with the standard derivatives. So this one is cannot solve with standard derivatives, right? It makes it more difficult because all the derivatives we have been learning, we haven't come across a derivative, a function where it's expressed in a particular variable and against the power of that same variable or a form of that variable itself. We haven't come across that, so we cannot solve with standard derivatives that we've been learning for the past few videos. So how will we tackle such a question? And this is where logarithmic differentiation would come in. Okay, so instead of chain rule, which I'm going to scrap away right here. Okay, we're not going to use a chain rule. Okay, instead what we're going to use is we're going to take the logarithm, the natural log on both sides. So we take ln y equals to ln sine x to the power of x. Okay, so this will lead us to ln y equals to x ln sine x. Okay, how do I achieve, how did I get from here to here, you might be wondering. And this is basically a basic law of logarithms. If you have a log, okay, a logarithm of let's just write in ln, actually it'll be easier. You can also write log to the base 10, it's no problem, but I'm just going to stick to ln. So if you have ln a to the power of b, it can also be written in the logarithmic rule as b ln a. So this is like a power rule in logarithms, actually. Okay, this is going back to stuff in pre-calc, where let's say you have the ln of a with a power itself, you can bring that power down and multiply it with ln a. So this is basically a logarithmic rule that we're using here, right? So now the next step is, of course, to do implicit differentiation, right, on both sides. You have to take the derivative on both sides, obviously. So implicit differentiation, right? So ln y would be what? It would just be 1 over y times dy dx. Whereas for this right here, you'll definitely need to use product and chain rule. So you need to use two rules, product and chain rule, to solve the problem. And frankly speaking, if I'm going to be very quick about it, so yeah, I'm going to be very quick about it actually. So it will be ln sine x times 1 plus x times ln sine x. If you differentiate the ln, it would be 1 over sine x, right, times differential of sine x would be cosine of x. So that would be 1 over y dy dx is equals to ln sine x plus x, and you have cosine over sine, which is just 1 over tan x, or we can say as cot x, right? Because we know that cosine of x over sine of x is equals to 1 over tan of x, and we know that is simply the cotangent of x, right? So upon rearranging the equation, we'll end up having dy over dx is equals to y times, well, this whole thing, right? So it'd be this ln sine x plus x cot x. And if I already erase this a little bit, let me just clear up some space right away. And yeah, I'm going to clear some space as well. It will be what? In this case, it would be, okay, so therefore your dy dx would be, y is what? Y was just sine x to the power of x multiplied with ln sine x plus x cotangent of x. So this is basically your derivative actually, and this is all thanks to implicit differentiation, right? And this is what we call logarithmic differentiation. Actually, we take the log of both sides, right? We take the log of the left hand side, okay, the LHS, okay, and we take the log of the right hand side, which is what we call as the RHS. So after taking the logarithms, of course, we will perform implicit differentiation, right? And eventually we do product rule right here, okay, to solve the problem, and we do some basic algebra, and we manage to get our answer right here. Okay, so this is basically logarithmic differentiation. All right, so it can be useful in certain complex functions like this, where you don't have the standard derivative and you want to find the derivative, you want to find what is the dy dx, so this would actually be very, very helpful. Okay, so now let's go to a couple of problems. Let's try to tackle some problems out right here. Okay, so the first problem, okay, we have a curve that is defined parametrically. So we have a curve defined parametrically, all right, parametrically. Okay, and it's given to us that x is just 2 cosine theta. So 2 cosine theta. Alright, so 2 cosine theta plus cosine of 2 theta. Okay, and y is given to us as 2 sine theta, okay, minus sine 2 theta. Okay, and they want us to find the equation of the curve. Okay, they want us to find the equation of the curve itself, right? They actually want us to find dy dx at theta is equals to pi over 4, right? So they want us to find that. All right, so I'll give you guys to pause this video and give it a try on how to solve this problem, and later I'll be back on teaching you how to solve the problem. Okay, so assuming you guys have paused and give it a try, let's try solving this problem. So the first step to do, right, is to obviously find the derivatives, right? dy over dt and dx over dt. We need to find those two first of all, right? So how do we find them? So for theta, right? Because our parameter now is in theta, so it would be in respect to theta. Okay, so in this case it would be dy over d theta and dx over d theta. So dy over d theta, it's just what? It's just 2 cosine theta minus cosine 2 theta times with 2. So it would be 2 cosine theta minus 2 cosine 2 theta. Okay, so that's dy d theta. Then for dx over d theta, all right, similarly is just negative 2 sine theta, all right, and here cosine 2 theta will become negative sine 2 theta times 2, so it becomes, well, negative 2 sine theta minus 2 sine 2 theta, right? Sorry about that, just pause for a bit. Okay, so the next step, right, to solve this problem is obviously to use a chain rule, right, to find dy dx. So to find dy dx, it's quite simply dy dx is just dy over d theta divided by, right, divided by dx over d theta. So it's just 2 cos theta minus 2 cos 2 theta, okay, over negative 2 sine theta minus 2 sine 2 theta. Okay, so that's your dy dx, but we're still not done because we still have to substitute a value, right? And in our case, let me just erase this real quick. Okay, so let me just erase this real quick, by the way. Okay, so in this case actually it would be right, so it would be theta equals to pi over 4. Okay, so we want to find dy dx at theta equals pi over 4, so it's very simple. We just plug and play the numbers, so it would be just 2 cosine pi over 4 minus 2 cosine theta, I'm sorry, 2 times pi over 4, my bad, over negative 2 sine pi over 4 minus 2 sine 2, oops, so we just write it down, okay, 2 sine 2 times pi over 4. So what's the answer gonna be? Angle unit, radian, okay, let's just put it like this. So 2 cosine pi over 4 minus 2 cosine 2 times pi over 4, so it'll be square root 2, okay, over, okay, so negative 2 sine pi over 4 minus 2 sine, okay, so it become negative 2 minus root 2. Okay, so this is your exact answer, by the way, actually, right? And yeah, that's how we solve this problem. But it's pretty straightforward. Okay, it was parametric differentiation. We first had to find the parameters dy over d theta and dx over d theta, and I think from these two parts we had to use a little bit of chain rule. I know I used the faster variation, the out and in method, but you know, it works, obviously, right? You don't have to really remember it. And of course you just use the chain rule again, because we know to find dy dx is dy d theta times with d theta over dx, but d theta over dx is just simply, well, 1 over let me just erase that real quick, is just, well, as I said before from the inverse law, is just 1 over dx d theta, right? So you can just simply have the division symbol right away, okay? And that's basically it. And once you get dy dx, you can immediately find a theta, which is just simply pi over 4 itself. All right, so that's the first question done. Now we're gonna proceed with the second question, which of course will be involving implicit differentiation. So I'm gonna be erasing this real quick. Okay. Okay. Okay, so let's go for the second question. So we're given an equation, by the way, and also the equation looks something, oops, let me erase it, let me run it in yellow real quick. Okay, so we have to find dy over dx at 1, negative 1, okay, on the curve, okay, on the curve, and the curve equation is given to us as x cubed minus y cubed minus xy minus x is equals to 0. So again, I'll give you guys to pause this video and try to work this out, and later I'll come back and obviously try to help you out with the solution. Okay, so assuming that you guys already paused the video and give it a try, so let's try to solve this problem. Actually, the first thing the question wants is to find the dy dx, right? They want to know what dy dx is. So again, the fastest way to take dy dx is to take the derivative on the left hand side, and of course to take the derivative on the right hand side, okay, to find the derivative of both sides. So as we try to find the derivative of both sides, what we end up with is 3x squared minus 3y squared. Remember, if you're differentiating with y, don't forget the dy over dx term. And this is xy, by the way, so this is interesting. So this one of course would entail us to use the product rule, by the way. So this one will involve us to use the product rule. So if you want to differentiate this, it would be y, right, times 1, because plus what would be plus x times dy over dx, because differentiating y is just 1 dy dx. So in this case it would be y plus x dy over dx minus 1 equals to 0. Okay, so in this case it'll be 3x squared minus 3y squared dy over dx minus y minus x dy over dx minus 1 equals to 0. So of course we have to rearrange the function. So the non dy dx terms I'm going to write here, negative 3x squared y minus minus 1, okay, equals to, and of course I'm going to highlight this in blue, the one that is dy dx terms, so it'll be just these two terms I'm circling in blue, right? And you will end up having 3y squared plus x, okay, times with dy over dx. And I'm gonna erase the earlier term because we want to find the dy dx, right? So in this case it would be dy over dx is just 3x squared minus y minus 1 over 3y squared plus x. Okay, so that's your dy dx actually. Now we're still not done with the question because the question wants us to find the dy dx at these coordinate points 1 and negative 1. So in order to do that, so at 1 and negative 1, okay, it's very simple. We just simply substitute the values. So dy dx is just 3 times 1 squared minus negative 1 minus 1 over 3 times negative 1 squared plus 1. So what's the answer going to be? So it's just 3 times 1 squared minus negative 1 minus 1 over 3 times negative 1 squared plus 1. So it'll be 3 over 4. 3 over 4. So that's basically your answer. Alright, so it's not too bad. You know, it's a very straightforward question actually. So let's go for 2 more questions, right? And this will involve the use of logarithmic differentiation, by the way. So let's try to target these 2 problems. Okay. So we're given a question, right? Y equals to x ln x, find dy dx. Of course, I mentioned earlier these 2 are related to logarithmic differentiation, so I think this should be pretty straightforward. I'll give you guys some time to pause the video and attempt the problem. Okay, so assuming you guys have paused and attempted the problem itself, let's try to solve this, find the derivative. Okay, so the first step we're going to do is to obviously take the logarithm on both sides. So you have ln y equals to ln x, the power of ln x, right? So therefore we have ln y equals to ln x times ln x. Okay, so it's quite simple really. So ln y equals to ln x squared, and once we do the derivative on both sides, what we'll end up having is we would have 1 over y dy dx, okay, implicit differentiation right coming, and we'd have here 2 ln x times 1 over x. Okay, so therefore once we do the differentiation, we get dy over dx equals to we'll get into 2y ln x over x, and since y is basically equals to x ln x times ln x over x. Okay, I know it's a little bit quick, by the way, because I have some stuff going on actually, so I apologize for the very rapid pacing. Okay, so it's x to the power of ln x, okay, times ln x. Of course we forgot the 2, so I've multiplied with the 2, by the way. Okay, so 2x ln x, okay, right? So 2x ln x times ln x over x. So if you want to further simplify the problem, we can write it like this, right? So it become dy over dx equals to 2x ln x minus 1 times ln x. Okay, so you can leave it like that. So hopefully that's the derivative of this function, right? We used to logarithmic differentiation. And let's do one last one before we conclude the end of this tutorial. Alright, so let me just erase this real quick. Okay, so last question of the day is this one. Okay, so we're having a function of of y equals to 1 minus x squared to the power of half times with 2 x squared plus 3 to the power of negative 4 over 3. So of course we were asked to obviously find dy dx. So how do we find dy dx actually? I'll give you some guys to take your time to pause the video and attempt this problem. Alright, try to use logarithmic differentiation, see if we can actually get any answers or not actually. Right, and yeah, let's report back in a while. Okay, so if you guys have attempted this problem, good, and if not, let's attempt the problem together. So what we can see is that we have two sets of functions, right? Y expressed in terms of 1 over x squared to the power of half and 2x squared plus 3 to the power of negative 4 over 3. Now you might be thinking, why not just use the product rule? Okay, why not we can use the product rule and solve the problem? Yeah, we can use the product rule and solve the problem, that is true. So yes, that is a viable method, but the question actually wanted us to use the logarithmic method. Okay, the logarithmic method. Okay, so they want us to use the logarithmic method. So let's actually use the logarithmic method and try to solve the problem. Alright, and let's see if it's a bit easier than the product rule or not. Okay, so to do the logarithmic method, we take the ln on both sides. So ln y equals to ln, okay, wow, we have a huge over function. So 1 minus x squared to the power of half times with 2x squared plus 3 to the power of negative 4 over 3. Wait, made a mistake with the brackets. Okay, so we're gonna simplify this function. Now one thing about logarithms actually, if you guys remember back in your middle school or your high school or college, is that if you have ln AB, it's equivalent to ln A plus ln B. Okay, so that's another logarithmic rule you guys have to remember. And also the last rule we've talked about is ln A to the power of n is equals to n ln A. Okay, so that's a power law and the addition a product law. Okay, so we're gonna of course split it into half ln 1 minus x squared, okay, plus or minus 4 over 3 ln 2x squared plus 3. Okay, then we do the implicit differentiation. We get 1 over y dy dx is equals to half times 1 over 1 minus x squared times negative 2x minus 4 over 3, which is just the constant itself, times 1 over 2x squared plus 3 times 4x. Okay, then we get dy over dx, which is just simply y times the whole thing, and y we know is being this function, so y multiplied with negative x, okay, over 1 minus x squared. How we know it's negative x? Well, because 1 over 2 takes it out, so it becomes a 1, right? So that's why we end up having negative x over 1 minus x squared, and we're gonna have 16x minus 16x over 6x squared. Actually, oh, never mind, we'll just leave it as it is. Okay, it'll be a bit complicated, I guess, if I were to multiply it. We just leave it as 2x squared plus 3. Okay, and of course, as we get the final answer, so dy dx is y being this function 1 minus x squared to the power of half multiplying with 2x squared plus 3 to the power of negative 4 over 3, and then you're obviously multiplying with this chunk right here, negative x over 1 minus x squared minus 16x over 3 2x squared plus 3. Okay, so this is our final derivative, okay, using logarithmic differentiation. And you might say, okay, product rule, might get something simpler, maybe, or you might end up getting the same derivative. You guys can give it a try and check it out. And I think that's pretty much about it for parametric functions and implicit functions, right? I hope you guys actually have a good solid understanding about these two type of functions and how do we differentiate them. So for our next video, okay, we'll focus a bit on optimization, and this will probably be the last part of this function and derivative series. This will be the last part actually, so this will be more of the finale of this part actually. And as usual, I like to say thank you guys for watching this tutorial. All right, and yeah, see you again soon. Bye.